Hello everyone, I'm Rahul Chowdhury and welcome to our comprehensive course on low-level design. Today we're going to embark on a journey that will transform how you think about software architecture and design patterns. We're starting with something truly remarkable, the Phone P story. This isn't just another theoretical lesson. It's a real-world crisis that demonstrates exactly why low-level design matters in the software industry. What you're about to hear is a story of a company facing complete extinction and how excellent design principles literally saved their business overnight. This is design excellence under pressure. Picture this scenario. The Reserve Bank of India suddenly banned Yes Bank, Phone P's primary banking partner. In one moment, Phone P, one of India's largest payment platforms, faced complete shutdown. Millions of users, thousands of merchants, all at risk. Here's where the miracle happened. Phone P managed to switch their entire UPI payment backend infrastructure in just one day. Think about that, a complete backend migration that typically takes months, accomplished in 24 hours. So what was their secret weapon? It wasn't luck, it wasn't just hard work, it was excellent low-level design. Their system was built with such modularity and abstraction that they could swap out critical components seamlessly. This story perfectly illustrates why we're here today. Good low-level design doesn't just reduce costs through efficient resource utilization. It can literally save entire businesses. It saves development time, enables rapid adaptation, and creates resilient systems that can handle real-world crises. Throughout this course, we'll learn the principles and patterns that made Phone P's miracle possible. By the end, you'll have the tools to build systems that are not just functional, but truly resilient and adaptable. Now that we've seen how critical good design was for Phone P's success, let's dive into the foundation of it, all understanding what low-level design actually is. So, what exactly is low-level design? Think of it as the detailed blueprint that tells us not just what we're building, but precisely how we're going to build it. LLD focuses on detailed implementation. It's all about the how of software systems. While others might sketch the big picture, you're the one figuring out every bolt, every connection, every interaction that makes the system work. The core elements of LLD include class organization, how we structure our code, method definitions, the specific functions and their signatures, and component interactions, how different parts of our system talk to each other. These are the building blocks that turn ideas into working software. Now, how does this differ from high-level design? It's the difference between architecture and implementation details. HLD asks, what components do we need? While LLD asks, how exactly will each component work and interact? Here's why this matters for your career. Low-level design skills are absolutely essential for SD-2 and higher roles. It's what separates junior developers from senior ones, and it's a crucial part of technical interviews. Master this, and you're not just writing code, you're architecting solutions. Now that we understand what low-level design is, let's dive into the foundation of quality software. Today, we're exploring the two fundamental pillars that separate good software from great software. The first pillar is code reusability. This is all about the principle of write once, use everywhere. When you write reusable code, you eliminate redundant implementations and create building blocks that can serve multiple purposes across your application. Think of it like creating a universal charging cable. Once you design it right, it works for multiple devices. In software, this means writing functions and classes that can be easily adapted and reused in different contexts without duplication. The second pillar is extensibility. This is your software's ability to adapt to change gracefully. When requirements evolve, and trust me, they always do, extensible code allows you to add new features without rewriting entire sections. Extensible design is like building a house with expansion in mind. You lay the foundation and structure so that adding rooms later doesn't require tearing down walls. No major rewrites needed when business requirements change. But what prevents us from achieving these pillars? Let's identify the enemies of good design that we must avoid. The two biggest culprits are tight coupling and hard-coding values. Tight coupling means your components are too dependent on each other. Change one thing and everything breaks. Hard coding means embedding specific values directly in your code, instead of making them configurable. The good news, we have a solution: design patterns. These are your toolkit for solving common design problems. They're proven strategies that help you achieve both reusability and extensibility while avoiding the pitfalls we just discussed. In the coming pages, we'll explore how to apply these principles practically. Now let's dive deeper into one of the most fundamental principles in software design: code reusability. We're going to explore the DRY principle, which stands for don't repeat yourself, and see how it works in real-world scenarios. Let's start with a concrete example that you've probably encountered. Think about date and time handling in your applications. Instead of writing custom date formatting code in every project, we use standardized packages like Python's DataTime or JavaScript's Date API. This is the DRY principle in action. We avoid duplicating the same logic across different parts of our code base. The benefits of following DRY are substantial. When you reuse well-tested code, you automatically get fewer bugs because you're not reinventing the wheel each time. Your testing effort is reduced since you only need to test the reusable component once. And perhaps most importantly, you get consistent behavior across your entire application. But here's where many developers fall into a trap: tight coupling. This happens when your classes become so dependent on each other that changing one requires changing multiple others. It's like a house of cards where touching one card brings down the whole structure. We need to be careful not to sacrifice flexibility for reusability. Another major pitfall is hard-coding values directly into your reusable components. Imagine creating a send email function, but hard-coding the sender's email address inside it. This kills reusability because other parts of your application can't use this function with different sender addresses. Hard-coded values are the enemy of flexible, reusable code. So what's the solution? Two key practices: parameterization and dependency injection. Instead of hard-coding values, make them parameters. Instead of creating tight dependencies, inject what you need from the outside. This way, your code remains reusable while staying flexible and maintainable. These techniques will become your best friends as you build more complex systems. Now that we've explored code reusability, let's dive into our second pillar of good software design: extensibility. This is all about building systems that can grow and adapt to future requirements without breaking existing functionality. Let's start with a concrete example. Imagine you've built a payment system for your app using Razorpay. Now your business wants to add Paytem as an additional payment option. With good extensible design, you can add this new gateway without touching any existing payment code. The system was designed to accommodate new payment methods from day one. Here's another powerful example: platform expansion. You've built an amazing Android app, and now you want to launch on iOS. With extensible architecture, you can reuse most of your business logic, data models, and core functionality. Only the presentation layer needs to be rebuilt for the new platform. The secret sauce here is plug-in architecture. Think of it like building with Lego blocks. Each component is modular and interchangeable. You can swap out pieces, add new ones, or remove unnecessary parts without affecting the whole structure. This modularity is what makes extensibility possible. Finally, let's talk about future-proofing strategies. The key is using abstract interfaces and loose coupling. Instead of hard-coding specific implementations, we define contracts that any compatible component can fulfill. This way, when new technologies or requirements emerge, our system can adapt gracefully. Remember, extensibility isn't about predicting the future perfectly. It's about building flexibility into your system so it can evolve naturally. When combined with reusability that we just covered, these principles create software that truly stands the test of time. Now that we've established the principles of reusability and extensibility, let's explore a fascinating evolution story: how programming paradigms have transformed over time to address growing complexity. Today, we're diving into the evolution from procedures to objects, a journey that fundamentally changed how we think about organizing code. Let's start at the beginning with sequential programming. In the early days, programs were written line by line, executing from top to bottom. While simple to understand, this approach had severe limitations. No reusability, no organization, and maintenance became increasingly difficult as programs grew. Then came procedural programming, which introduced functions to bring order to the chaos. Functions provided reusability. We could write once and call multiple times. They also improved organization by breaking complex problems into smaller, manageable pieces. But then we hit the breaking point. As software systems grew more complex, we encountered entities that were too sophisticated for simple procedural approaches. Traditional functions struggled to handle complex real-world concepts effectively. Let me illustrate with the classic animal management problem. This example perfectly demonstrates why we needed to evolve beyond procedural programming. In procedural programming, managing animals required multiple parallel arrays. Name array, id array, sound array. Each animal's data was scattered across these different arrays, connected only by a common index. Adding new animals meant updating multiple arrays, and ensuring they stayed synchronized a true maintenance nightmare. This pain point led to the revolutionary concept of object-oriented programming, where related data and behaviors could finally be grouped together logically. Next, we'll see how classes provided the blueprint solution to this organizational challenge. Perfect, now we arrive at the solution to all those organizational challenges we just discussed. Classes, the blueprint revolution. This is where object-oriented programming truly begins to shine. Think of a class as a blueprint, just like an architect's blueprint for a house. The blueprint itself isn't a house, but it contains all the specifications needed to build one. A class serves as a template for real-world entities, and here's the revolutionary part. It groups both data and methods together in one organized container. No more scattered functions and variables. Let's look at a concrete example with a student class. This blueprint defines what every student object should contain. Notice how the student class contains data like name, ID, age, and grades, alongside methods like study, take exam, and get GPA. Everything related to a student is now organized in one logical place. Here's a crucial distinction. The class is the blueprint, but an instance is the actual object created from that blueprint. One student class can create many student instances, each with their own specific data. This blueprint approach solved the fundamental problems of procedural programming. No more scattered code, no more difficulty in maintenance, and perfect organization of related functionality. Next, we'll see how these blueprints come to life as objects. Now that we've seen how classes serve as blueprints, let's explore the next crucial step, bringing these blueprints to life as objects. This is where the magic of object-oriented programming truly begins. Think of the factory analogy we've been building throughout our course. A class is like a mold or blueprint in a factory. But what good is a mold if we never use it to create actual products? The class represents the mold or blueprint. It defines the structure and behavior. Objects are the actual products manufactured from that blueprint. Each product is real, tangible, and independent. The instantiation process is fascinating. When we create an object from a class, the computer allocates memory specifically for that instance. Each object gets its own independent space to store data. This memory allocation ensures that each object maintains its own state. Changes to one object won't accidentally affect another object of the same class. They're completely independent entities. Here's a perfect example. John student and Mary student are both created from the same student class blueprint. They share the same structure and methods, but each has their own unique data and identity. This independence is crucial. John's grade changes don't affect Mary's grades. Each student object maintains its own state while following the same behavioral patterns defined by the class. Understanding this object instantiation process is fundamental to mastering object-oriented programming. You're creating real, working entities from abstract blueprints, turning ideas into executable reality. Next, we'll dive deeper into the building blocks that make these objects so powerful. Now let's break down what makes classes so powerful by examining their fundamental building blocks, attributes, and methods. First, we have attributes, also called fields. These are variables that store the actual data of our entity. For example, in a user class, attributes might include name, date of birth, and age. These hold the state, the current information about that specific user object. On the other side, we have methods. These are functions that define what our entity can actually do. Methods like update name or calculate age define the behavior. They're the actions our object can perform, often using or modifying the attributes we just discussed. This separation is crucial. Attributes hold the data. Methods define the actions. Together, they encapsulate both what something is and what it can do, keeping related data and behavior in one cohesive unit. Now that we've explored attributes and methods individually, let's bring them together to see the complete picture. This is where everything starts to click. First, let's clarify what we mean by class members. Class members are simply the combination of attributes and methods. That's it. Together, they form the complete blueprint of what our objects can store and what they can do. But here's where it gets really interesting: object state. The state of an object is simply the current values of all its attributes at any given moment. Think of it as a snapshot of the object right now. Let me show you this with a concrete example using our student object. Watch how the state changes when we call methods. Here's our student object before calling any methods. The state shows name is Alice, age is 20, and grade is A. This is the current state, the snapshot of all attribute values. Now we call the update name method with the parameter Bob. This method call is about to change our object's state. And here's the result. The state has changed. Name is now Bob, while age and grade remain the same. Notice how only the name attribute was modified by our method call. This demonstrates a crucial concept. Object state is dynamic. It changes over time as methods are called and modify the attribute values. Each method call can potentially transition the object from one state to another, creating a living, evolving entity in our program. And here we are at the final stop of our low-level design introduction. Let's take a moment to appreciate how far we've come together in this session. We started with Phone P's incredible success story, how proper low-level design enabled them to scale from a startup to processing billions of transactions. Then we explored the fundamentals of object-oriented programming, understanding how classes serve as blueprints and objects bring those blueprints to life. We built a solid foundation by learning the two pillars of good software code: reusability, through the dry principle, and extensibility for building systems that can grow. These aren't just theoretical concepts. They're the bedrock of every successful software system you'll encounter in your career. Looking ahead, your journey into low-level design is just beginning. You'll dive deep into design patterns, the proven solutions that experienced developers use to solve recurring problems. The solid principles will become your compass for writing clean, maintainable code. This knowledge will transform your career trajectory. You're moving from thinking like a junior developer who just writes code to thinking like a senior developer who designs solutions. This mindset shift is what separates good programmers from great software architects. You're now ready to write software that doesn't just work today, but stands the test of time. Software that can evolve, scale, and adapt to changing requirements. This is the power of good low-level design, and you're well on your way to mastering it. Great work today, everyone.